Early melting and bridge formation leads to a lot of cases of hanging and slipping. Let's take one case. Let's begin with the melting behavior of body material. Acid pellet and some lumps will start melting early around 1000 to 1100 degrees centigrade, while flux pellet and basic center melt later. This early softening can cause premature collapse and bridge formation. Higher FeO and basicity in slag also lower liquidus temperature. If injection coal has high ash, it forces higher basicity, which can hinder melting point drastically. Now coming to this slide, which is about reduction, degradation, and fines, is also very important. During hematite to magnetite reduction, sinter and lump ore structure can break down, generating fines. This is called reduction degradation, or many times it is also pronounced as low temperature breakdowns. These fines resist gas flow, slow heating, and form ring of poorly permeable material, ideal zone for bridge to form. Insufficient gas reduction is also a very big bottleneck. When gas reduction is poor due to moisture, fines, or irregular descent, material reach the tuyere zone with excess oxygen. Direct reduction direct reduction then consume coke rapidly, as we know in direct reduction, and pushing the cohesive zone downward. This unstable melting behavior increase the risk of chilling and bridge formation. Now coming to the scabs, channeling and sleeping is also very important phenomena. Scabs in the cohesive zone and mixed layer of ore and coke disrupt gas flow drastically. Channeling, where gas flow through least resistance, causes uneven heating. Below the bridge, coke is consumed and ore melts, creating voids. Eventually, the bridge collapses, causing a slip and disrupting furnace structure immensely, which again the layer structure and refresh starts takes a lot of shift to become normal. Coming to this slide, which is about immediate action after the sleep, and in which after a sleep we have to restore the layer structure. Just now what I was mentioning, operate on reduced blast volume is a easy process to take care of such type of abnormal situation, and this reduction we may have to continue for 5 to 10 hours depending on intensity of the hang and slip. Many times hang slips restore a longer period, and there we need to operate at reduced blast for a longer period. So this stabilizes the furnaces and prevents repeated hanging and sleeping cycles. Typically it takes 6 to 8 hours to regain a stability, but many times in a bigger furnaces it become repeated for it continue even 48 hours or 2 days, and it really a matter of a great patience for operator to restore to normalcy. Now, preventing measure for burden descent, uh, we can say that hanging and slipping often stem from poor burden descent. The cohesive zone glues material together. Preventive action focus on maintaining smooth descent and avoid bridge formation. That should be our motto in order to take care of such type of hanging. Controlling A process differential is very important. So keep the process differential within 1.6 to 2 bar as recommended in a routine practices. If blast pressure is too high, reduce blast volume while maintaining top pressure. This stabilizes descent and prevent erratic behavior, and which is also important. Top pressure we can of course reduce if optic temperature remains very less, that is below 100, and in that case we may relieve top pressure. Otherwise top pressure we must have to build so that burden descent remains downward. Now coming to the thermal control and overheating, which reduces the downward forces and increasing slag holdup. Monitoring the heat balance and the direct reduction trend helps in combating the coolness effect or the direct reduction domination in the furnace. And if cooling is detected, we have to increase PCI by 10 to 20 kg per ton hot metal. In severe cases, charge extra coke to lift the cohesive zone in faster way. However, here many times we have to decide that till what time we have to continue PCI. Then if the flame temperature remains around 2100 to 2200, within this range, even though after increasing the PCI, then it's well and good. But if the flame is coming down with the increase of PCI, below this we must have to increase coke rate as quick as possible, or we may add a extra bunch of coke to lift the cohesive zone faster. Now coming to the cast house and liquid levels management, or we can say the casting management. High liquid levels increase buoyant force, compressing the cohesive zone. Maintain the low level through a continuous alternate casting is a good way out. For poor slack drainage, using larger drill bits dia, switch tap holes or overlap casting, these all are a better method to combat the situation. Prevent coke mess by lowering wind and plugging leaks. Coming to the burden quality and preparation, we have to limit fines below 3% using proper screening. Proper screening. We have to limit fines as we have mentioned earlier also. We have to select the material with a good reduction degradation resistance. Distribution of fines evenly is a good game changer. We must have to distribute the burden across a wide range of cross section, and this leads to a thinner ferrous layer with a distribution of the fines material evenly across the cross section. So pressure loss will be almost uniform across the cross-sectional area. We have to blend burden component well and add non-softening material like nut coke, which act as a spacer, or if possible HBI to improve permeability. Burden distribution and gas flow adoption is also key. We have to adopt a ideal burden distribution like ore-free center, horizontal layer, and sufficient wall coke, and maintaining a coke layer thickness at least more than 150 centimeter to ensure gas and liquid flow at the post level. Uh, so to avoid inverse profile and control central flow for efficiency, it's required to focus all above methods and need to do in a faster mode. Now to prevent channeling, as we know, channeling disturb or disrupt uniform heating. Prevent it by ensuring a stable, ideal burden distribution, a stable descent, and proper blending. So addressing fines concentration and scab formation proactively is a good strategy to combat furnace and to bring it to normalcy. Moisture management is one of the very important aspects. Using moisture gauges for coke, pallet, and maintaining top temperature above dew point is a game changer. If condensation, evaporation cycles occur, increase the gas volume or lower the top pressure to remove water vapor, and this is a good way out. And this is also a good knowledge sharing for the operators at what phases, at what stage top pressure is to change. And coming to the alkali and zinc control, we can say that monitoring alkali and zinc input to prevent a scaffold formation is a very important aspect. And reducing fines, cleaning a scaffold by lowering burden level, promote central gas flow to eliminate these elements with the top gas will drive the furnace towards normal, and productivity also normalize by concentrating in all these areas. Coming to the wear protection, we have to use sensors and cameras to detect wear blockages, prevent scab formation by ensuring timely melting, support wears to avoid tipping, and maintain adequate slag basicity to prevent burning is the must.